In this video, we talk about the intermediate value theorem. So the zeros of most polynomial functions cannot be found by factoring. The ones we work with will involve factoring, so we're good to go. We can find them by hand, but that's not typically the case. So while we may not be able to find the exact zero, we can use a property of continuous functions to know where a zero is located. So continuous function, just for very simplistic terms, means if I can draw the graph without having to pick up my pencil, right? It's a smooth, continuous graph. It keeps going. There's no holes or jumps in it. And so this intermediate value theorem states that if f is a continuous function on a closed interval from a to b, let n be any number between f of a and f of b, such that f of a does not equal f of b. So remember, f of a and f of b are just some y values for an x value of a and some y value for an x value of b. We have these two y values, f of a and f of b, and n is some value in between them. So a and b are the corresponding x coordinate for that y value. So then there is a number c in the interval a to b such that f of c is equal to n. And that's because between the a and the b, the graph is smooth, right? There's no jumps or gaps in it, so it has to go through every single one of those y values between f of a and f of b. So we can use the intermediate value theorem to determine if an interval contains a zero. So let's let a, b be an interval such that the values of f of a and f of b are opposite signs. So that means one's going to be positive and one will be negative. Remember, these are the y values that we're talking about. Then by the intermediate value theorem, there is a real number c in the interval a to b such that f of c is equal to 0. Right? So 0 is between any positive and negative number. And so there's got to be some value of x that corresponds to that y value of 0. And so we can use the intermediate value theorem to prove the existence of a 0 on an interval. We cannot use it to disprove the existence of a 0, because I have a picture of a graph here where we have a point a, f of a, and a point b, f of b, where f of a and f of b are both positive on my graph. If I just saw, oh, there's no sign change, I might think there's no 0 between them, but it just depends, right, because of the two values of a and b that I found for that interval. But if I look at the graph, it actually may cross the x-axis somewhere between that a and b. So I can't use it to say there's not one. I can use it to prove that there happens to be one. So when f of a and f of b are different signs, we are guaranteed a 0 on the interval of a to b by the intermediate value theorem. If there is no sign change between f of a and f of b, we have to use a graph or other methods to determine if there is a 0 on the interval. So example 6 is to use the intermediate value theorem to explain why there is a 0 in the interval 3 to 4 for the function p of x equals x cubed minus 4x squared plus 2. 3 is my a and 4 is my b, so I need to look at what is f of a or f of 3 and what is f of 4. And if I can see there's a sign change, that is if one's positive and one's negative, then I'm guaranteed that there's a value between 3 and 4 for which the y value is 0. So f of 3 is 3 cubed minus 4 times 3 squared plus 2, which would be 27 minus 4 times 9 plus 2, or 27 minus 36 plus 2, which is negative 7. Then f of 4 is 4 cubed minus 4 times 4 squared plus 2, which is 64 minus 4 times 16 plus 2. But 4 times 16 is 64, so 64 minus 64 plus 2 is 2. So notice that f of 3 is -7. F of 4 is 2. So that means on a graph, f of 3 equaling -7 is the point 3, -7. And then f of 4 equals 2 corresponds to the point 4, 2. So because my graph is a continuous function, right, it's a polynomial function, the graph is going to have to go through some 0, which occurs between the values of 3 and 4. And I could use my graphing calculator to actually confirm that as well.